Okay, thanks. So yeah, I'm going to be giving a survey on MCSP. What's the survey going to be like? So I'm going to be focusing mostly on a few important papers in the area and mentioning the main questions. So it's going to be sort of a conceptual map of the area, especially for those of you who haven't seen the problem before and don't really understand why people are working on it. I hope to give some motivation. So that's what Eric said yesterday when he presented his result. He said the motivation will be tomorrow, and you'll get more motivation than you need, probably. So let's get started. So what is MCSP? So here's the most basic version of the problem, right? So Eric already defined this yesterday, but I just want to make sure we're all on the same page. So the input is just a truth table of a Boolean function on n bits, on little n bits. So the truth table is of size 2 to the little n, so let's call that capital N, and you're given a parameter s, right? And the question is, does this Boolean function represented by this truth table have a circuit of size at most s, right? So this is just the basic version of the question. And there are lots of variants you could ask, several of which are interesting in their own right, and there are interesting relationships between them. One natural kind of variant of this is, well, why do we care only about Boolean circuits? How about circuits of other kinds, right? So we can ask more generally, if you have circuits from a class C, does F have C circuits of size at most S, and call that C MCSP. And in fact, in general, you can talk about other complexity measures. So it doesn't just have to be circuit size, or for some class of circuits, it could be some of the measures we've seen already earlier in the workshop. So it could be approximate degree, it could be communication complexity, your favorite complexity measure. For all of these measures, the analog of this problem is interesting, right? Okay, so this is the decision version of MCSP. So you're asking whether F has small circuits. There are also several other questions you could ask. So you could, for example, ask, given the function, what the smallest circuit size is, right? That's optimization version. And if you can solve the decision version, you can use binary search to solve the optimization version. So that you could also ask the search version, right? So there's a very kind of natural kind of object which witnesses that F has a circuit of size at most S, namely the circuit itself. So given F, you could ask to find a circuit of size at most S. So that's the search version. And in some cases, we'll be interested in an approximate version of this, where we don't want, we relax the requirement that we ask for the precise circuit computing the function, and are happy with it computing the function on most inputs, right? So that's the search version. We could also ask, for example, the average case complexity version. So we might not we might not need to solve this problem on all inputs. We might be happy solving it on most inputs in some sense. And this will come up later in the talk, and it'll be kind of an important part of the connections to other areas of complexity theory. And we could also not give F explicitly. So this is giving you a lot of information, right? You're giving the entire truth table of F and asking whether it has small circuits. You could just give some set of inputs of F together with the values of F on those inputs and ask whether that's consistent with a small circuit, right? So this problem is very closely related to learning theory, because you want to know whether there's a small hypothesis consistent with your set of samples. And that will be an interesting question as well, though we won't be talking about it very much in this survey. So these are just some of the variants of MCSP we'll be looking at. So this is a low bound semester, and well, my argument is that if you're interested in low bounds, you should be interested in MCSP, because every low bound is a no instance of MCSP, right? So every low bound is somehow, for some complexity measure, saying that there's that function which doesn't have a small complexity measure. Okay, but it still doesn't really tell us why we should be interested in the complexity of MCSP. I mean, why do we need to study MCSP as a computational problem, and how would that help us? So just in general, problems like MCSP tend to be very informative. So knowing about the complexity tends to give us a lot of information because of somehow this meta-computational nature that the problem has, right? So you're given kind of an instance, and you want to know about some kind of, like, the instance itself encodes an algorithm or a question about an algorithm, and you want to know about that. So somehow the question is, does there exist an algorithm to decide if some kind of algorithmic question is true? And questions of this sort tend to be very important in computer science in general and complexity theory in particular. So for example, there's a SAT question, right? So SAT question is also this kind of a meta-computational question where you're given a circuit and you want to know whether it has a satisfying assignment. And these problems, actually, SAT and MCSP, can be thought of as sort of duals of each other because in SAT, you're given a circuit and you want information about it. So you want to know if the circuit is satisfiable. In the counting version, you want to know what the number of satisfying assignments is. For QBF satisfiability, you perhaps want to evaluate some formula on the truth table computed by the circuit. In general, there are various kinds of information you want about the truth table computed by a circuit, and those give you variants of SAT. In MCSP, it's just somehow the inverse question, right? You're given the truth table and you want to know whether there are small circuits. SAT somehow corresponds to kind of white box questions where you're given a computational object and you want to know about the function computed by it. And MCSP corresponds to black box computation. You're given the function as kind of an oracle in some sense, and you want to know about small representations of it and about complexity questions about the function. And our understanding of SAT has sort of paid off in many ways, right, throughout complexity theory. So one of the earliest results was the Cook-Levin theorem, and the NP completeness of SAT led to understanding the complexities of many other problems in relation to SAT. Then there's kind of the Cook-Rekha program and proof complexity, which is also kind of focused around SAT. There's the PCP theorem and all its implications for the hardness approximation. More recently, there's sort of Ryan's approach to using algorithms for SAT to prove low bounds. So in all of these cases, somehow having more information of the complexity of circuit SAT helps us gain somehow a better understanding of complexity theory. And I'd like to argue that somehow MCSP should be equally useful in terms of things that we figure out about it. So it's a problem that's much less well studied than SAT for various reasons. I'll explain some of them. But if we do figure out more things about it, I think the benefits would be quite significant. So there's just maybe a couple of other sort of perspectives or ways of looking at MCSP that I'd like to mention. One is this kind of perspective in terms of of individual strings and their complexity and whether they're random or not, right? So in some sense, you're asking whether, so this truth table is essentially a string of length 2 to the little n, and you're asking if it has small complexity. And whatever complexity measure you choose, any reasonable measure you choose, a random string is not going to have small complexity, right? So a random string is going to be a no instance. And kind of like somehow some structured instances are going to be yes instances. So in some sense, this is asking whether our input is random or not. And this is kind of a perspective that kind of connects the problem to questions in computability theory where there's a column of random strings and you want to know whether a string is column of random or not. And to kind of various other questions in between complexity and computability theory. And Eric actually has several excellent surveys adopting this perspective and looking at what this tells us about the complexity of MCSP. But I won't be saying much more about that here. And even if you don't care about somehow these kind of meta-computational questions, maybe MCSP is interesting just because it's just a question of compressing strings. I mean, a circuit is just a compressed version of a string, and you're extracting the string from it in kind of an implicit way by evaluating the circuit at each input. And the question is, are there short descriptions of this form? And because circuits are simple combinatorial objects, somehow this is a simple combinatorial problem, which we're trying to understand. That's maybe some other perspective of MCSP, which might not be that useful, perhaps. Okay, so that's a kind of a few kind of questions, perspectives on MCSP. So that's so far has been sort of philosophical. So I'd like to kind of make things more concrete now and try to tell you about the connections that MCSP has to other parts of complexity theory, for what the main questions are, and so forth. So something that's quite easy to see for any natural version of MCSP is that MCSP is an NP, right? Because you're given the truth table and you want to know the small circuits. You can just guess a circuit of size at most S. And you can just evaluate it on each input and check that it computes this truth table correctly. And because the truth table is a large object of size 2 to the little n, this is only going to cost you time like S times 2 to the n to verify once you've guessed the circuit. So, so MCSP is an NP problem.
In particular, if S is small, then you can do this.
Exactly, yeah. So,
finding 2 to the S times 2 to the n.
Right, exactly. Yeah. So, or 2 to the s, yeah, or 2 to the o tilde of s. So it's really an FPT in some sense. So if you think of this as a parameterized problem, and s is a parameter, it's an FPT because it only depends exponentially on the parameter, not on your input. Right? So related to that, even though for most of the talk we'll be thinking about MCSP with a parameter included, in some cases it'll be useful, convenient, or in some rare case even important to think of the unparameterized version where we have fixed size function, and we want to know about MCSP of s where this s is fixed as a function of n. So for example, you could think of MCSP of n to the point 1, capital N to the point 1, which is really asking whether the truth table has circuits of size 2 to the point 1 times little n or not. So, I mean, clearly, and this question reduces to this one, but yeah, it's sometimes very interesting to consider this. Okay, so we've seen that MCSP is an NP, and as Avishai said, it's even an FPT. But it's an NP hard, right? And this is somehow the central question about MCSP. So I'll be spending the first part of my talk, talking about that, about the possible NP hardness of MCSP. And it seems that there's no kind of way of solving MCSP without looking at all possible circuits, right? We don't really get much information from checking whether some circuit kind of solves. If it doesn't solve MCSP, we don't really get information about other circuits. So it's sort of unclear how to solve MCSP better in exponential time. But yeah, I mean, that's just a very naive thing that we're trying. Maybe there are more clever ways of doing it. So so this question of the NP hardness is kind of a question that presents itself almost immediately. And then the other question is, well, if we don't manage to prove NP hard, can we at least get evidence that it's not in P? Is there something you can say about whether or not MCSP is in polynomial time? So that's something else that we'll look at. And we'll look at other structural features. So other features of NP problems in NP. And we see that MCSP behaves somewhat unusually with respect to these features. So, and the way we will kind of present this is to look at it in comparison to SAT, right? So SAT has lots of different features which we understand quite well. And we'll kind of like do a comparison on a case-by-case basis of what's true for SAT and whether the same kind of thing is true for MCSP or not. And if not, what does it say about MCSP, right? So throughout the talk, have in mind kind of SAT as a case to compare with regard to things I'm talking about. Okay. So the first thing I'm going to talk about is actually after the intro is this question of explicit constructions quite briefly because it'll come into the question of NP hardness, right? So what's an explicit construction? So let me just define it. So an explicit construction is just an algorithm that allows you to get your hands on inputs, yes and no inputs of different lengths, right? Explicit. So explicit construction for a property Q, which is just a set in 0, 1, a set of strings in 0, 1, is a polytime computable F. Let's say that this F takes kind of unary inputs and goes to 0, 1 star, such that we want for all n, f of 1 to the n to be in Q intersect 0, 1 to the n. So let's just ignore the cases where Q is empty on some input lengths, as it is for MCSP when the input length is not a power of 2, then, I mean, clearly there's no yes instances. Let's just restrict ourselves to instances for which Q is non-empty.
The range of F is 0, 1
star, sorry. So this is what an explicit construction is. So you give the input length in unary, and when you give that, there's an efficient procedure which computes for you some string that's in Q, right? And it's fairly easy to see that natural NP complete problems. So if L is a standard NP complete problem, so natural NP complete problems. L and L complement have explicit constructions, right? So if you think of SAT, vertex cover, clique, and so on, it's pretty trivial to give a construction of a yes instance or a no instance of each input length, right? That's completely trivial. So part of what's complicated about MCSP is that even this very kind of standard feature of many natural problems in NP is kind of related to one of our main open questions, right? So it's just a proposition. Explicit construction. So for the complement of MCSP, where we maybe take the unparameterized version, so let's say n to the point 1, equivalent to E. So this is not too hard to see. Yeah, I mean, yeah. So it's a fairly short proof. So yeah, if you have an explicit construction of something that's a hard truth table that doesn't have circuits of size n to the point 1, that's going to give you a very hard function in E. So that's kind of a fundamental kind of problem in circuit complexity, which we are quite far from solving. And the converse is true as well, right? So even getting explicit constructions for kind of this problem are very hard. And somehow this difficulty underlies some of what prevents us from gaining a better understanding of MCSP in general, as I'll explain later. But this is just quite a simple example of that. So I should just mention in passing that, so yeah, for natural NP-complete problems, the language and its complement have explicit constructions, but there are natural problems in P for which we don't yet know this, right? So if you take, for example, primes, which is a problem in P, we don't have explicit constructions in polynomial time for that. If you take Ramsey graphs with optimal parameters, we don't have polynomial time constructions for that. So some of the complexity of deciding Q isn't always kind of correlated with how easy it is to have an explicit construction. Yeah, so there's some properties for which, which are easy to decide, but we only know explicit constructions under deramization assumptions, and others which are very hard to decide, but for which explicit constructions are easy, right? And I think Valentin might say something more about explicit constructions in the talk later in the morning. Okay, so any questions about this? So this is just a very kind of a simple starting point. Comparing SAT and MCSP, SAT and SAT complement have easy explicit constructions, but MCSP does not, right?
Are you also interested in gap versions of MCSP?
Oh, yes, yeah. So I should have mentioned, so yeah, when I was mentioning all the different variants, I should have mentioned also the approximation version, right? So where you want to know, so instead of given a parameter, instead of being given just a parameter S, you're given parameters C and S, and you want to know, say yes if the circuit size is at most S, no if it's at least C. And in fact, this sort of approximation version and the relationship between C and S will be important in the last part of the talk. So yeah, so that's an important question too. Yeah. Okay, yeah, that's all.
So I think this raises a general issue that we should probably be more aware of, even though we all know, which is that there's a big difference between computational difficulty and computational expressibility. And we tend to conflate, or the notion of completeness says that in many cases these coincide, but that's not true all the time. So problems that are more expressive we think of as having higher complexity, but that is only a weak indication that they're more difficult than other problems.
Right. For example,
and there are many problems that are difficult but not expressive.
Right. So for example, the ability to easily find yes and no instances might indicate it's harder to show average case hardness. It might relate to average case hardness, for example. I mean, so that might be one kind of thing that is related to. But yes, yeah. So yeah, it's a good point, and especially relevant to MCSP. Okay. So that's as far as explicit constructions go. So now let's get to the main kind of question about MCSP, the main open question on which most of research in the problem has focused. This question of NP-hardness. So yeah, so it's just, is MCSP NP-hard or not? And so MCSP is sort of a very kind of interesting case here in that it's a natural example of a problem for which we have no strong evidence either of NP-hardness or the problem isn't NP-hard, right? So we know that if we take a problem of our choice, a problem that we happen to encounter naturally, then it's quite often either in polynomial time, it's easy in some sense, or it's NP-hard, right? So that's a phenomenon that we see in general. There are some problems that don't seem to fit into this. So for example, factoring, graph isomorphism. But for these problems, we have evidence that they're not NP-hard. I mean, they're NP-hard, the polynomial hierarchy collapses. There's some complexity theoretic evidence that these problems aren't NP-hard. So MCSP is sort of an unusual example of a problem for which so far we don't really have much evidence either in favor of NP hardness or against it. So in some sense it's wide open, and if you ask people working on the problem, then they'd all probably have different beliefs about whether it's NP hard or not. I certainly believe it is, but there might be others who don't. So what is it about MCSP that makes this kind of NP hardness question tricky or hard to understand? So kind of a important insight into this was from this sort of paper by Valentin and Ginny Sai on the circuit minimization problem. So this is in 2000, and this is really the paper that got research on MCSP kind of going again. So MCSP has a very kind of rich history in some sense because there's a lot of work on it in the Soviet Union in the 50s and 60s. You can read about some of this in Trachtenbrot's survey. So it's a very natural problem from the perspective of circuit minimization, and it was looked at, but I think, well, there just wasn't much work because it's hard to know what to say about the problem in a formal sense. In fact, I mean, Eric reports that Levin delayed his publication of his NP-completeness result because he hoped to show something about the NP-completeness of MCSP. He couldn't do that, and we still don't know how to do it. He did say something about DNFs, but MCSP in general is still wide open. But this paper of Valentin's and Ginny somehow brought the problem kind of into focus again and had some kind of very interesting insights into it, especially into this question of NP hardness. Kind of an important result in that paper, so this is from Cabinet's side, is that we can't, it's going to be hard to give the sorts of NP hardness reductions that we used to, right? So when we want to prove that a problem is NP hard, we find gadgets, we kind of construct a reduction that works. And the sort of thing that works for other NP problems isn't going to work in a straightforward way for MCSP, right? So what they show is that if there are nice M reductions, and the core of their result is really that there's this sort of explicit construction obstacle for MCSP, right? We don't know how to explicitly construct no instances of MCSP, and this sort of kind of lack of knowledge on our part translates to a lack of knowledge on how to construct reductions. And let me just sort of explain how that goes. Kind of like, let's just take the version of MCSP where we have the parameter set to say n to the 0.1. So we have sat. And we have MCSP complement. So there's MCSP with some set parameter. Okay, so we need to somehow control the kinds of reductions that we use to be the sort that were typically used. And our notion of nice for this kind of toy result somehow will be that the reduction doesn't shrink the input that much. So that's all we need. So it's a polynomial time reduction, and it doesn't shrink the input too much. Because it's a reduction, it maps SAT complement to MCSP complement and SAT to MCSP. But as I said before, for natural NP-complete problems, there are easy explicit constructions. So there's an easy explicit construction of unsatisfiable formulas. There's trivial ones. Just compose a construction with the reduction, and you'll get a hard function, right? So it's a very simple idea, but I think it has very interesting implications. Because it's the sort of result that really raises questions. So what does it really say about NP hardness, right? So it says that there aren't nice, it doesn't really say that NP hardness is likely or unlikely. It's just saying that it's hard to show, right? And it sort of raises the question, what is it about these reductions as a problem? Is it that they're M reductions? Is it that they're nice? If we kind of strengthen the notion of reduction, can we still show results of this form? If we weaken it, can we just rule out reductions unconditionally? It sort of raises a whole host of questions about the kinds of reductions we can hope to use, and what the notion of reduction has to do with hardness and showing hardness, right? So this actually led to sort of like a long line of work. Just give you a few examples. So for example, there's Ryan and Cody Williams, then There's Hitchcock and Pavan. There's Shuichi and Osamu Watanabe. There's Eric, Dheeraj, and Valentin. So I think there's Eric and Shuichi, and so on and so forth. So there's been like a long line of works where you kind of play with the notion of reduction you have here. You see what kinds of consequences we get. So they're trying to show that even for kind of weak notions of reductions, somehow you get some sort of complexity implication from a hardness result, which we don't know how to show, right? And I'll just maybe kind of mention one result out of these, because it kind of rules out reductions of a certain form, and that's this result of Cody and Ryan's. So they say there are no n to the 0.1 local reductions from parity to MCSP. So what's a local reduction? A local reduction is just one that looks at a few of the input bits, right? And in fact, the known Np-Hardness results that we know, almost all of them work under these local reductions, under these D-log time uniform projections, where you only look at a few bits of the input and then you decide what the output bit of the reduction is. And what Cody and Ryan show is that even if you will allow this amount of locality, you won't even be able to reduce parity to MCSP. And it sort of uses a similar idea to the kind of cabinet psi idea, but it's just that what they do is to show that if there is such a reduction, then you can have small AC0 circuits for parity, and that's a contradiction. Somehow you can take advantage of the locality to kind of get small circuits. And other interesting aspect of this result is that there's no sort of niceness constraint, right? So they eliminate this niceness constraint. So this just works for any reduction as long as it's local. So this is kind of like a clear result. It shows that there's certain reductions that just don't work. I mean, we have a lot of freedom in terms of which notional reduction we use. And it seems to me that the root of the difficulty is really this explicit construction obstacle, right? These results all seem to take advantage of that. So what if we somehow given kind of a hard truth table for free? Does this help us at all? So I think that's a very natural question. So let's... It's a question. Is MCSP NP hard? So there's some work on this when the reductions are very simple, for example, constant depth circuits, but when they can be polynomial size circuits, there's essentially nothing known, as to the best of my knowledge. So, and this is, I think, a question that's possibly quite interesting to think about regard to NP hardness.
Wouldn't Larry Williams apply even under non-uniform reductions?
Sorry?
Since they're getting a contradiction with the non-uniform
yes, so their result is for non-uniform reduction, but it's on the local reductions, right, which are very simple. So here, if you allow polynomial size, I mean, it doesn't.
Well, in fact, uniformity is pretty crucial in the Murray-Williams result.
Well, I guess they need to construct these circuits, right, from the reduction. Is uniformity crucial or not, Ryan? Do you remember?
Determinism is not crucial. Like the Warbound holds are randomized awards.
But uniformity is.
Yeah, I think so.
It's not just locality, but yeah, kind of like
Because it's a non, you know, they give a non. They show that there's no reduction from parity, and non-uniformly there is a reduction to, well, not MCSP but MKTP. Show me the difference between those two.
Yeah. So perhaps uniformity is crucial there. I mean, so it's not completely clear to me, but yeah, certainly for non-uniform reductions, we don't really know. I think. Yeah. You had a question?
Are you insisting on many one reductions?
No. So there's also some of these negative results, the ones I mentioned, involve kind of like other notions of reductions, truth table reductions. I have some recent work with Mike Sachs about Turing reduction. So there's like a range of reductions that are considered. So that's another possibility, of course. I mean, if you kind of like allow the use of Turing reductions, but there I don't really expect it to help you very much. I think non-uniformity randomness is more what's likely to help. Okay, so so that's the status of the MCSP problem for general circuits. But we could kind of like look at it different ways. So we could consider, so we've defined CMCSP, and we could look at some simpler classes of circuits, right? So it seems that the reason why we're unable to show Np-Hardness results is because we don't know how to show superpolynomial circuit low bounds. But there are lots of models for which we do know how to show superpolynomial circuit low bounds. I mean, for DNFs, for AC0 circuits, AC0 mod P, and so on. So if you consider these models, do you get maybe kind of a hardness result if you look at the kind of low bound techniques in the proper way? So what's the complexity of MCSP? For weaker P, for weaker C. And there's, so it's a bit unintuitive actually, because you would think that if you're asking about a weaker circuit class C, the problem should only be easier. I mean, the circuit class is more complex, kind of knowing whether there's a small circuit from that class or not should be a harder problem. But we don't know any way to make this formal, so it's not clear how to make that formal. I mean, of course, it's true for satisfiability. If you have a larger class of circuits, then the problem gets harder. But here, if the class of circuits gets larger, it's not clear that kind of like a simpler class of circuits, MCSP, reduces to MCSP for a larger class of circuits. And that's because, well, if you have a function of low kind of complexity for some simple class of circuits, of course, it's still simple for the harder class, but the other way around, it's not so clear how to get a reduction, how to transform hard functions for an easy class, for a simple class of circuits, to hard functions for a more complicated class, right? So somehow it's kind of a non-monotone notion, at least as far as we understand it. CMCSP's complexity is not quite monotone in C. So, and in fact, for DNF MCSP, we do know quite a bit. So this has been known for quite a while, since the 70s. So DNF MCSP is NP. And somehow this isn't so surprising, because what is the complexity of deciding whether a truth table has small DNFs or not? What you want to do is really cover the truth table, kind of the ones of the truth table, by a set of subcubes, which are all one, right? Because each term of the DNF corresponds to a subcube in the Hamming cube, right? A subcube which is all ones, where you're setting some of the variables to zeros and ones, and the rest are left free. And you have an OR at the top in kind of a DNF, which is just the union of these kind of subcubes. So this question is really whether you can cover the ones of the string by a set of one subcubes. And that's sort of essentially a set cover problem. And it's kind of a structured version of the set cover problem. And you can reduce set cover to this problem, and that's what Masek did. So his original reduction was quite complicated, but it was simplified in later work. I think Eric and Tony are involved in some of this work. And it's known to be NP-complete, and not just that, it's known that you can approximate the problem to a factor n, right? And that just follows from the fact that it's a specific set cover instance. So there's a specific set cover instance underlying it, and just by solving the set cover instance approximately, which we know how to do, you can approximate the problem. So just to re-emphasize what approximation means, it's a question that you all asked about if there's a gap, right? So so if there's a circuit of, you want to distinguish between having circuits of size s and not having circuits of size s times some k, and here k is little n. So let me just use capital N, log n. Yeah. Okay, so so that's something. So at least there are versions of a natural class of C for which is NP-complete. But I mean, we know low bound techniques for many more classes, right? Not just DNFs. So what can we say about more general classes? So not very much, it seems, at least so far. But it might very well be that people just haven't looked at this very much. I don't know. It's certainly worth looking at in more detail. So that's sort of a recent result of mine with Igor and Shuichi. So the DNFs of XORs. It's just a slightly more complicated complexity measure that MCSP is NP-hard. But yeah, this is just a little bit of progress, and I mean, there's still a lot left to do. So for one question is, what about AC0 circuits, right? So and let's kind of give some flexibility with the notion of reductions. So let's say quasi-polynomial time reductions, because we don't yet know how to show explicit functions that have purely exponential size AC0 circuit low bounds, only sub-exponential. So let's allow the reduction to be a bit weaker, so quasi-polynomial time reductions. Yeah, so I think this is a good question. And in general, I think in terms of trying to understand a circuit class C, I mean, yeah, after all, as complexity theories, we're trying to understand complexity measures. So they're sort of proving NP-hardness results for C MCSP, where C is as general a class as possible, is an interesting direction, because in some sense you're saying something about the about all functions and their C complexities. So with the low bound result, you're just saying that here's one function or sequence of functions that doesn't have small circuits. Here you're talking about all functions in some sense. So it gives you more information. So I think it would be very interesting for the known low bounds to try to use the techniques there. I'm not quite sure whether you can do it in a black box way, but maybe using the techniques used to prove these low bounds to extend them to show hardness results for C MCSP for larger classes C.
So first is your mean for every depth, for every constant depth?
Yes. Yeah. So yeah, fix a depth, and you want to show that question whether F is small A0 depth D circuits is hard. Yeah.
In the NP completeness, even the simpler one, DNFs, do you look at the parameterized version or just the unparameterized version? And is it enough to take S to be a polynomial, let's say?
It's enough to take a fixed S as a function of n. So yeah.
This fixed n is a polynomial in little n or polynomial in big N?
Polynomial in big N.
Big N.
Yes. Yeah.
It's not.
Well, I mean, you could scale it down, so you could probably show under ETH that it would be hard for that case. Yeah.
Do you have an hardness approximation for DNF of parity?
Yes. No. So yeah, we can kind of approximate it in quasi-polynomial time to within the same approximation factor, and we also have hardness approximation result, which doesn't match the positive result. It's like log n, polylog n. So there's some gap there still. Yeah, I should mention that here there's also been quite a bit of work on inapproximity results, not just showing that DNF MCSP is NP complete, but it's hard to approximate the circuit size to within smaller than log n factor. And there's a line of work stemming from kind of work in PCPs and learning theory, which gets a handle on this. I think it's known that it's hard within to approximate within factor log n to 1 minus epsilon, as far as I know. Yeah, under some assumption, the standard assumption. Okay, so yeah, so that's about the sort of the hardness of MCSP, the NP hardness or hardness under standard for standard notions of hardness. So now let's look at the question of whether MCSP is in P and what evidence we can give against it, right? So far we have this NP hardness result, but for MCSP in general, for Boolean circuits, we have no evidence at all that it's not in polynomial time. I mean, from what I said in this talk. So let's look at that question. Okay, so yeah, so is so let's say this is section 3. So or maybe that was section 3 already. So average case complexity. So the question of whether MCSP is in polynomial time or not, somehow the work on it has also given us information about the average case hardness of MCSP, and I'll tell you what it means for MCSP to be average case hard, pseudo-randomness, and there's connections with pseudo-randomness, and the famous natural proofs paper of Rasbrov and Rudich. Yeah, so I guess one of the contributions of the cabinet psi paper I mentioned earlier is pointing out what the natural proofs obstacle has to say with complexity of MCSP. And in fact, for me at least, that's been the most productive way to view that paper. I mean, we think of it usually as kind of a barrier result saying certain proof techniques don't work. But I think in terms of getting information about MCSP and its status as a computational problem, that's for me the real kind of contribution of that paper. So yeah, the question we're asking is MCSP in polynomial time or not? And we want to give evidence against it. So kind of the key notion that gives us kind of some insight into this question is the notion of natural proofs due to Rouse-Brown-Rudich. So, so what is a natural proof? So a natural proof useful against. So let's say we have a class of circuits C, and we have a size parameter S. A natural proof useful against C of S is just a dense polynomial time subset of the hard functions. Right. So let's say these are all truth tables. Let's say these are all the hard ones. And a natural proof is just, so these are the hard functions. And these are the easy ones. And natural proof Q is just polynomial time decidable subset of the hard functions that's dense, that has significant kind of fraction of its weight on the uniform distribution over inputs, right? So that's just an interpretation of natural proofs in terms of MCSP. Well, I mean, one kind of observation is that this corresponds to a very natural notion of average case easiness for MCSP under the uniform distribution, right? So if you just take uniform distribution for zero error algorithms under the uniform distribution, this is essentially what it means for a natural proof to exist, right? So Q is in polynomial time here, and Q is dense. So here's the sort of observation that I had with Shuichi in a paper from last year. Natural proofs. Useful. Is equivalent to MCSP of S. Easy on average. Algorithms. So what does it mean to be easy on average for zero error algorithms? You just take the uniform distribution. So this is over the uniform distribution over UN. So you just take the uniform distribution, and you want to either give the correct answer or you want to say you don't know, right? So that's a zero error algorithm. And what it means to be easy on average is that you just do this with a significant probability over the uniform distribution. So it's an inverse polynomial probability. It's pretty easy to see that if there are natural proofs, then you get such an algorithm, right? Because if you just check membership in Q, and if it says yes, then you say yes. Otherwise, you just say don't know. And this solves the MCSP with a significant fraction of the uniform distribution. And the other way around just follows from the fact that MCSP is so kind of biased somehow, because most functions are hard functions. So if you have a zero error algorithm, you just sort of throw away the inputs on which you get a zero, right? And you're still left with a significant fraction of inputs, and so you get a natural proof from that, right? But I think looking at things in this way, in terms of the average case easiness of MCSP, is somewhat useful. So what did Rouse-Brown-Rudich show? So Rouse-Brown-Rudich showed that under a standard cryptographic assumption, if so that's exponentially hard. One-wave functions exist. no natural proofs. So under a standard kind of cryptographic assumption about one-way functions that are very hard, there are no natural proofs that are useful against polynomial sized circuits. And in our terminology, it just means that MCSP is hard on average, right? So this cryptographic assumptions implies that MCSP is hard on average. I mean, of course, natural proofs have kind of several other implications, the motivations from proof complexity, and so on. But for the purpose of this talk, I'll kind of just kind of restrict attention to what it implies for MCSP. And well, how does the proof go? So once you have the basic ingredients, it's fairly kind of straightforward. Kind of here's just a proof by picture. So it's well known that based on exponentially hard one-way functions, that you can construct pseudorandom function generators, which are kind of a family of pseudorandom functions where each function has small circuit complexity, but no kind of efficient test can distinguish such functions from random ones, right? So let's just take such a family of pseudorandom functions. So they're all in this easy set, right? Because each of these pseudorandom functions has small circuit complexity. But if you have a natural proof, then because the natural proof is in polynomial time, that's an efficient test which distinguishes random functions from pseudorandom ones, right? Pseudorandom ones, none of them is in Q, and random ones, a significant fraction of them is in Q. So under this assumption, you have that there are no natural proofs. So it's kind of very straightforward once you have the required machinery. I mean, to go from one-way functions to pseudorandom function generators, you need this result of Goldreich, Goldwasser, and Micali. But yeah, I mean, beyond that, it's fairly straightforward. And in fact, you can get more generally if the pseudorandom functions computable by circuits from a class C, then C MCSP is hard on average, right? I mean, it's just the proof just goes through the same way. Okay. So that tells us something about the likelihood of MCSP being in P. Under cryptographic assumptions, we don't expect that to happen.
But this is somehow distinguishing, is very important to distinguish polynomial time for quasi-polynomial time.
Right. So
it's sort of delicate as opposed to the...
Yes, that's a good point, but there's a trade-off. So if you only assume like super polynomially hard one-way functions, then you get there's no natural proofs against kind of MCSP with a parameter that's polynomial n to the epsilon, right? So under that assumption, you'll get that MCSP with n to the epsilon parameter is hard on average. So there's a simple trade-off between, in terms of how you construct random functions, there's a trade-off. And so I'm just stating kind of the version of it which rules out even this kind of like much simpler version of CMCSP, but it's true. Yeah, there's kind of a parametric kind of trade-off. And I mean, one of the nice things about kind of thinking about CMCSP on average is that there's this feature I mentioned before of MCSP that we don't know how to relate kind of C MCSP to C prime MCSP when C and C prime are different. We don't know how they're reduced to each other. But clearly, if you look at an average case notion, if C is a simpler class, then if C prime MCSP is easy on average, so is C MCSP. I mean, that's fairly easy to see, right? Because I mean, a random function is going to be hard even for the harder class, and an easy function is going to be solved by the algorithm for the harder class, and therefore also for the easier class. So when you look at average case complexity, you get this kind of monotonicity in terms of the complexity of CMCSP, which is good. And you also get sort of natural kind of relationship between CMCSP for a parameter S and for a parameter S prime, where S and S prime are different. Eric mentioned this yesterday, that we don't really know in general how these relate to each other. But the average case notion, it's trivial to see that if you can solve CMCSP of S prime, for S prime bigger than S, then you can also solve CMCSP of S on average, right? Yeah.
Regarding the observation, you can also use it in the other direction, right? So we have natural proofs against AC0 and DNFs and stuff. Because then you would get that it's easy on average.
Yes, yeah. So
but it's hard on the worst case, right?
Yeah. So yeah, for DNFs, for example, right? For DNFs, it's NP hard in the worst case, but natural proofs tell you that it's easy on average. So there we have kind of a gap, right? So there's an NP hardness result for the precise complexity, but on average, it's easy. Yeah. And yeah, we might expect that even for larger class of circuits that it's hard in the worst case, but
that follows directly from the fact that you have an approximation algorithm.
Also, yes, yeah. So it also follows from the fact that you have an approximation algorithm. But the easiness is also true for AC0, for example. Yeah, MCSP AC0. Yeah. But I'm going to get to this later. So I mean, this is a key part of what Russell, Valentin, Antonina, and Marco did. This kind of connection to learning. So hopefully there'll be a little bit of time to discuss that as well. Okay, so
I guess this also tells, you could also apply these observations to classes in which we believe there are one-way functions. So it means that we expect TC0 MCSP is not in P, right?
Right, exactly. Even on average, right? So somehow, what these results tell you is that MCSP is a sort of problem where if you prove like a result in the average case, for C that's big enough, we don't really know how to distinguish the average case from the worst case for like polynomial-sized circuits. So if you tend to prove negative results, it tends to go through in the average case as well, which is perhaps the reason why we aren't able to prove stronger results, because maybe, it's a harder problem. So, okay, so there's this result, the Rahul-Rudich result, and this is what it says about MCSP. In terms of class of Boolean functions, so this is in respect to one-way function assumption. So Eric and Bireshwar Das had a result about SZK. So SZK is just statistical zero knowledge. It's a class of functions that have zero knowledge protocols that can't be distinguished even statistically from uniform. And that's in BPP to the MCSP. So there's probabilistic reductions to MCSP. And we believe there are problems in SZK that are not in polynomial time, so this gives evidence just from a Boolean complexity point of view that MCSP is hard. And notice that we are using probabilistic reductions here. So probabilistic reductions are useful in this context at least. Okay, so this is kind of like, so the proof, my proof sketch is like really simple, but I think it has, so this general framework has quite deep implications, and it kind of indicates like connections between pseudo-randomness and the complexity of MCSP, because essentially we're saying if cryptographic pseudo-random generators exist, then MCSP is hard on average, right? So there are these two regimes of pseudo-random generators. So there's a complexity theoretic ones where your generator is allowed to use more resources than the adversary, and the cryptographic one where the adversary can run a time polynomial in the size of the time of the generator, right? And these are fundamentally different. So Avi and Noam Nissan had constructions of complexity theoretic generators based on hard functions in exponential time. For cryptographic generators, we know them based on one-way functions. And for example, if NP equals P, you can break any cryptographic generator, but that actually implies that complexity theoretic generators exist. So there's like a significant gap between these two notions. So hardness and exponential time is closely connected. It's almost equivalent to these complexity theoretic generators existing. And here we see that if cryptographic generators exist and MCSP is hard, so I think a natural conjecture to make is that there's an equivalence. So we can ask, is this actually an equivalence? So is there an equivalence between the existence of one-way functions and MCSP being hard on average for zero-error algorithms? And if this were the case, it would be very interesting because it would give a natural problem, MCSP, for which hardness on average in a natural sense is equivalent to one-way functions. So let me just pose that as a question. So can we reverse the direction of Rahul-Rudich? Can we show that so Rahul-Rudich showed that if one-way functions exist, then natural proofs don't exist. But can we also show that if natural proofs don't exist, then one-way functions exist? So, question. One-way functions. So is the existence of one-way functions equivalent to MCSP? And I have some recent results in this direction, but I don't have proof, positive answer to the question as yet. But I think it's quite interesting that looking at the right kind of, like, it's a very natural distribution for MCSP, and the average case complexity seems closely tied to pseudo-randomness. Okay, so in the
So I think there should be a refinement to this question, a little bit technical, but it should be equivalent. The easiness of MCSP should be equivalent to the non-existence of non-uniform families of one-way functions versus uniform adversaries.
Right.
So this is what I would be.
You would believe that that's
a stronger statement of one of the directions.
You mean the Rahul-Rudich result also establishes that, and so you can yeah. But it could be that these two are equivalent too. So that's I don't know of any kind of evidence against that. Maybe we should talk about it. But yeah. Okay, so now let me say a little bit about the connections with learning. I've mentioned like 2 important papers in this area. I mean, there's several others, but the Cabinet-Tsai paper and the Russell-Rudich paper. And I want to talk about this a little bit about this recent work of Valentin, Russell, Antonina, and Marco. So let's first see what does learning have to do with MCSP, right? Yeah, let's go back to the comparison with SAT, right? So yeah, I should just mention in passing that this whole kind of like consideration of the average case complexity of MCSP, natural proofs, the non-existence of natural proofs is some of the analog for MCSP of Feiger's hypothesis for SAT. And we've seen that Feiger's hypothesis for SAT has lots of implications in hardness of approximation and so on. So I think one can expect that similarly looking at natural proofs and the hardness of MCSP, one might get similar implications. That's just in terms of extending this comparison with SAT. But for learning, so what is learning essentially? So the question, so I've given Oracle access to a function. So there's just, of course, one setting in which we do learning, but it's a setting that will be most relevant to us. Find small hypothesis for F. That explains F, right? So yeah, you're given Oracle access to a function and you want to kind of quickly find a small hypothesis that's consistent with F on most inputs. So that's one natural setting in which we do learning. And if you look at MCSP and the search version of MCSP, it's sort of clear that there's a close relationship here, right? So you're given the truth table of a Boolean function, and you can use that to simulate any sort of black box access you have to a function. And given that, you want to produce a hypothesis, namely you want to solve the search problem. You want to find a small C circuit that's consistent with the function. For learning, often the requirements in complexity terms are quite strong. You want to do it very efficiently. Here you have time that's a polynomial in the size of the truth table, so you have much more time. But this kind of relaxed version where you're trying to find small circuit in time polynomial size of the truth table is essentially a search version of MCSP. So search version of MCSP relates to learning. Certainly learning algorithms are likely to give us information about it, but there's connections in the other direction too. And there's sort of like a really cool recent result of CIKK. So what they show is that natural proofs, or in other words, the easiness on average of MCSP implies learnability, right? So MCSP. So what do I mean here? So MCSP is easy on average. We already defined what that means. What do I mean by the search version can be solved approximately? I just mean that, well, here to solve the search version precisely, we want to get a circuit of size S that represents the function exactly. Here we are happy with having a circuit that is correct on most inputs, right? So it's kind of a good approximation to the function and kind of Hamming distance, a small Hamming distance between the truth table corresponding to the object you output here and the function f. And that's the setting that you often have in learning, right? So I mean, it was open until this paper how to get kind of search to decision reduction even for MCSP, right? It's easy for SAT. If you know how to solve SAT in polynomial time, you can find a satisfying assignment just by setting bits kind of incrementally and checking satisfiability. So there's an easy search to decision reduction for SAT. And this is completely open for MCSP. It's something we didn't know at all for MCSP. And now we have kind of a version of it, which is sort of interesting because we are not even using that MCSP is easy generally, only that it's easy on average. And we're solving kind of the search version approximately from it. But it's very interesting because there are kind of versions of this result, so it's sort of implicit in this paper, but there have been kind of extensions. So Shuichi has kind of a recent paper on it, and there's some observations that other people have made that this actually gives kind of like an average case to approximation connection, right? So if MCSP is easy on average, you can actually approximate the circuit size of a Boolean function within some factor. As of now, this connection only works for approximation factor that's capital N to 1 minus epsilon or something like that. So that's quite large as a function of the truth table size. But I think a very interesting question is how close can this connection be made? So in general, for NP-complete problems, we don't have connections between average case easiness and and decision or even approximability. So this is a big question in complexity theory. But MCSP, being kind of the unusual problem it is, has this feature, and I think it's something that needs to be studied more closely. What is the best approximation factor that we can get for solving MCSP, given that MCSP is easy on average? So that's another question that I have. Okay. So I don't have much time to say something on the proof of this, which is also very interesting and again goes through pseudo randomness. But let me just mention in the last couple of minutes or so a few things about questions about lower bounds. So the question here is, what unconditional low bounds can we show for MCSP? Right? So for SAT, if we have a low bound for an explicit Boolean function, we can quite often use efficient reductions to SAT to get a similar low bound for SAT, and similarly for other NP-complete problems. But for MCSP, it seems to be like not as straightforward to show low bounds. So there's kind of a result of Eric's from a while ago, which shows that MCSP is not an AC0. And even that relies on Nissan-Suran generator, so it kind of follows by looking at Nissan-Suran generator against AC0 and analyzing that. But it's still open, even if MCSP is an AC0 with parity. So this is something that Eric mentioned, but I thought I'd re-emphasize it because I think it's something that we should be able to solve, and we don't know how to. So MCSP seems like a very hard problem. AC0 parity is a class that we seem to understand fairly well, but we're not able to separate MCSP from AC0 parity. What we are able to do, so in joint work with Shuichi, is get some formula low bounds. So MCSP of n to the little o1 is not in formulas of subquadratic. So MCSP with kind of like the parameterized version where it's kind of sub-polynomial doesn't have small formulas, so it requires quadratic size formulas. So we can say something about formulas. We don't get the best formula low bounds, which are nearly cubic, but we have close to quadratic low bounds. For A0 of parity, we can't say anything at all. And just as sort of like a lead-in to kind of Igor's talk, which is next, let me just mention a recent result with him and Jan Peek.
Is this De Morgan formula or a full basis formula?
Oh no, that's a De Morgan formula. Yeah, we don't know how to do it on a full basis. The superlinear low bounds are open. Okay. So if we could do this, so if we could get superlinear low bounds against circuits, n to the 1 plus epsilon, then this would imply that NP not equal to P. So even superlinear circuit low bounds for this problem would imply that NP not equals P. So I mean, of course, if we could carry through this connection for formulas, then we'd get NP not an NC1, but we don't know how to carry through the connection for formulas. For formulas, we can prove the low bound. For circuits, we know how to do the connection, but of course, low bounds are out of reach. So it's kind of interesting, perhaps indicating kind of other barriers towards proving low bounds, and I think that's something to be thought about more. So I guess talked about a few connections between MCSP and kind of other areas in complexity theory. There's a lot that I wasn't able to talk about. So there's connections with proof complexity, with algebraic complexity, with common complexity, as I mentioned earlier. And there's going to be a reading group this semester on MCSP. We'll be looking first at the Cabinet Psi paper, then CIKK, and maybe other papers. So if any of this interests you at all and you're here for longer, do come along to that. But that's all I have to say for now.
We're
running a little into our break time, but let's go ahead and ask questions.
Yeah.
So I think the CIKK result has some bearing on your question about equivalence to one-way functions, because the best we know how to do, as far as I know, assuming the non-existence of one-way functions, is a very average case notion of learning, whereas this is a worst case notion of learning.
Yeah, so this is the paper you have with Leonard Levin on the average case. Yeah.
There was like another paper by Alvin Blum et al.
Right.
I forget who the other authors are.
Right. But as far as I can see, I mean, this question is perfectly plausible. Perhaps there's, I mean, thinking about it more, perhaps it might not be. But if it's true, I think it would be very interesting because it would connect average case complexity to cryptography in a very interesting way. But yeah, I agree that it's not completely clear if it's true or not. I mean, I have some partial results, and yeah, it's still open. Yeah.
I think Avi a while ago had results with David Chow on this, but I forget what they were.
Was it right?
That were related to like learning versus one-way functions.
I mean, that might have to do with the hardness of learning hypothesis, right? I mean, there's like, yeah.
You don't think it was relevant?
Yeah, I don't think that it's well, okay. Yeah, I don't see it.
Any other questions?
So do you feel like MCSP is going to help to settle some of the major questions in complexity theory, or is it just a problem you're interested in solving?
No, I think both. I mean, certainly it's kind of lagging behind in terms of like, there's some low bounds we know how to use to show things about MCSP, but I think the connections with pseudo-randomness, etc., are likely to be useful in kind of low bounds approaches. So yeah, there is kind of a connection both ways, I think. Yeah.
Do you think that maybe one can prove some dichotomies that for like simple circuits it's hard because you can sort of generalize the DNF proof, but for like more expressive circuits it's hard because of the one-way function?
Yes, so that's a very interesting question. So there's a gap, right? So for DNF MCSP or slightly more than that, we have evidence of hardness from Np-Hardness. For like TC0 depth 4 and higher, we have evidence for cryptographic hardness. But what about in between? We don't have any evidence of hardness at all so far. So at least that we should be able to bridge in some way, hopefully. I mean, so that's I think that's an interesting question. But yeah, it's for very simple complexity measures like decision trees, and it's kind of easily doable. MCSP is kind of in polynomial time or quasi-polynomial time. So at a certain point where DNS it becomes NP-hard. I mean, my own belief will be that it stays NP-hard for circuits, but it's going to be not so easy to show.
Last call for questions. Thank you.